Okay, so now we are on tape. שלום לכולם, אני גדי, ראש בית ספר למדעי המתמטיקה באוניברסיטת תל אביב. אני שמח מאוד שזו הפעם השנייה שאנחנו מקיימים את הטקס של הענקת פרס שלום אברבנאל למתמטיקה שימושית. בזמנו התלבטנו מה הדרך הנכונה להנציח את שלום, והיו לו הרבה תרומות במתמטיקה השימושית בארץ, בקידום אוניברסיטת תל אביב ודברים נוספים. אחרי הרבה התלבטויות התגבשנו על פורמט של כנס דו-שנתי של מתמטיקה שימושית בארץ, שבמסגרתו יוענק פרס שלום אברבנאל למתמטיקאי שימושי מצטיין בישראל. השנה היה מתוכנן להתקיים הכנס, אבל הוא בוטל לאור הקורונה, אבל החלטנו לא לוותר לא על הענקת הפרס ולא על ההרצאה וכו'. האפשרות להעניק את הפרס ולקיים את הכנסים התאפשרה לאור תרומה נדיבה גם של משפחת אברבנאל וגם של גיורא ירון, אז אני מאוד מודה להם על התרומה שאפשרה לנו גם לתת את הפרס וגם לקיים את הכנסים. הכנס הבא יתקיים בעוד שנתיים. זהו, אני רוצה עכשיו להזמין את דוקטור גיורא ירון לספר מספר מילים על שלום. אז גיורא, הבמה שלך.
זהו. אז חברים, קודם כל תודה על ההשתתפות ותודה על ההזדמנות לומר כמה מילים על שלום. אני הכרתי את שלום למעשה שהוא כבר היה פרופסור אמריטוס של אוניברסיטת תל אביב. אני הייתי באותה תקופה יושב ראש של הוועד המנהל של אוניברסיטת תל אביב, ובפעילויות היומיומיות שלי, מה שנקרא for profit, אני עמוק בעולם הסטארט-אפים. וגיליתי חסר אדיר באנשים שמכירים ומבינים מחשוב מקבילי. אני חושב שאחד הבודדים פה על המסך שבאמת בא מתוך זה שאני מכיר, זה יוסי עצמו, אז אני לא יודע אם זה בא משלום או שזה בא מתוך יוסי, אבל הוא מה שנקרא גדל בתחום. ויש חסר אדיר בכוח אדם, ולי היה ברור שאם אין תשתית, אז גם לא יהיה כוח אדם. אז חייבים להקים תשתית. עכשיו, אני עצמי לא בא מעולם המתמטיקה השימושית, אני בא מעולם הפיזיקה, אבל פיזיקה טובה, ודאי תיאורטית, אי אפשר היה לעשות אילולי היו המחשבים של הימים ההם, הגולם ודומיו. ואז היינו בין 5 המדינות שהיה להם כוח מחשוב על, והיום אנחנו אפילו לא נכנסים לרשימת 500 מדינות עם מחשוב על. בקיצור, נשאלה השאלה איך מגיעים לשם, התייעצתי עם אנשים, אמרו לי, את שלום אתה מכיר? אמרתי, לא מכיר. אמרתי, טוב, תכירו לי אותו. ולמעשה זו הייתה פגישה של מה שנקרא אהבה מבט ראשון. אז קודם כל, מי זה שלום שאני הכרתי אותו? קודם כל, הוא איש של מעשים. יש כאלה שמדברים, בסוף לא יוצא עם זה כלום. שלום זה לא ככה. שלום אמר, תוכו כברו, לקח על עצמו לעשות משהו, אין אצלו. הוא שם את הצלב על המטרה, הוא כמו סכין חדה, יורה קדימה. מאוד הרשים אותי, כי זו תכונה שלא תמיד מקובלת אצל אנשים בעולם האקדמי. העולם האקדמי, בוודאי המתמטיקה השימושית, זה מחברת, אולי קצת מחשוב, אבל זה לא ניהול אנשים ולקחת פרויקטים ולגרום להם לקרות. אז היכולת למצוא מישהו שהוא גם עמוק בתחום, וגם עם יכולות ניהוליות ואפליקטיביות, זה לא תכונה שמוצאים אותה אצל הרבה אנשים. עכשיו, שמחתי לראות שהוא מהאנשים היותר מקובלים וידועים, לא רק בארץ, כי ארצנו די קטנטונת, למרות שאנחנו חושבים שאנחנו היחידים שהם אור לגויים, אלא בעולם כולו. רצינו להקים ועדה מייעצת, שלום כתב לנובליסטים לאנשים מהליגה הפותחת של עולם המתמטיקה, כולם נעשה ונשמע. שלום, תגיד לנו מה צריך לעשות, אנחנו פה בשבילך. היה לי ברור שלמרות שאני לא בא מהתחום, שאנשים שכן באים מהתחום, ויש להם יכולת to evaluate יכולות מתמטיות, מכירים בו כאחד מההורים והטובים שבתחום. עכשיו, תכונה אחרת ששבתה את ליבי זה האנרגיה האינסופית של שלום. אני חושב שזה גם עזר לו קצת לבלפף את מערכת הביטחון, שהחזיקה אותו כיועץ, אני חושב שהוא היה יועץ למערכת הביטחון שהגיל שלו היה הסם של כל היועצים האחרים במערכת הביטחון. פשוט היכולות שלו היו בלתי רגילות, התרומה שלו הייתה בלתי רגילה, ולכן מצא את עצמו כיועץ של מערכת הביטחון, למרות גילו הלא צעיר. אז הוצאנו דוח, שלום, אני והוועדה, ולמעשה נכשלנו, כי לא הצלחנו להשיג את המימון שחשבנו שצריך. אבל, סיכומו של דבר, העולם נכנס לחרדה בעולם ה-AI, Artificial Intelligence וה-DL, Deep Learning, וכנ"ל מדינת ישראל שלא רצה לפגר, וביג סופרייז, אי אפשר לעשות, כמו שאי אפשר לנסוע מתל אביב לחיפה בלי כביש, ככה אי אפשר לעשות AI ו-DL וכיוצא בהם בלי מחשבי על. הוגש דוח של תת ועדה שהוקמה לטפל בנושא AI ו-DL, שהתשתית לדוח הזה זה למעשה הדוח שאנחנו כתבנו, ורצה אלוהים, ואני כבר מתחיל להאמין באלוהים, שבדיוק היום פורסם בעיתונות שהתקציב ל-AI אושר. אז הכנס הזה נקבע ביד מכוון, או שלא ביד מכוון, בדיוק ביום שבו אושר התקציב ל-AI, שסאב סקשן שלו זה כמובן התשתית, שזה נייר שאותו שלום, אני ושאר חברי הוועדה הוציאו. אז בזה אני רוצה לסיים. מסתבר שהעבודה הנמרצת ששלום השקיע לא הייתה לחינם. זה שאושר תקציב זה עוד לא אומר ש-the money is in the bank, אבל זה אומר לפחות שיש הכרה שאם אנחנו רוצים להיות בעולם ה-AI, בעולם ה-DL, בעולם האפליקציות הכבדות, צריך את התשתית הזו. שלום בהיבט הזה ראה את הדברים הרבה לפני כולם, אבל במקום מסוים זה לא מפתיע אותי. אז שוב, תודה על ההזדמנות להגיד כמה דברים, ואני מחזיר את המיקרופון אליך גבי.
תודה כיורה, ואני מזמין עכשיו את פרופסור איתן תדמור לדבר. איתן היה יושב ראש ועדת הפרס של שלום אברבנאל לשנה הזו.
שלום לכולם, שומעים אותי, אני מנחש, אני איתן תדמור, נמצא קצת רחוק, אבל זה רק כמה אלקטרונים רחוק מכם. אז אני מדבר כאן בשני כובעים, אחד בתור אחד מ10 תלמידיו של שלום, והכובע השני כיושב ראש ועדת הפרס, אז תרשו לי לומר כמה מילים קודם כל בתור תלמיד לשעבר של שלום. שלום היה רקטור האוניברסיטה ב-77-80, ואלו השנים שבהם אני השלמתי את לימודי הדוקטורט תחת הנחייתו. קצת מילה אישית, אף פעם לא יצא לי לומר את זה, שלום היה בן גילו של אבי, הם אפילו סיימו את אותו בית ספר תיכון ב-48, כך ששלום היה עבורי במקור גם מנטור, אבל גם איזו דמות חינוכית ביותר ממובן אחד. זה היה שם איזה עירוב בין אבי ושלום, אותו שטנץ. שלום גילם איזה שיווי משקל בין מתמטיקאי שימושי, ובמובן הרחב יותר, כמו שאני רואה את זה, מדען שימושי, שהאמין בעיקר במידול וחישוביות הרבה לפני שזה הפך להיות מיינסטרים. אני מעולם לא פגשתי את גיורא ירון, אבל זה מעניין שאני רציתי לציין פה שהוא היה איש ניהול של אנשים, ואישיות שבאופן טבעי נתון לראות בה כגורם מוביל מתוך איחוד וחתירה לתמימות דעים. אני זוכר את זה בתור תלמיד, בתוך העדפה על פני המפריד, וחשבתי שבימים אלו, באמת איפה האנשים האלה. בקשר לגישה של שלום, בקשר למדען שימושי, אני יודע שהוא אמר את זה יותר מפעם אחת, לפחות לי, שהוא באמת ראה בלימודי המתמטיקה את שער הכניסה למדעים, מאחר ושזה השפה של המדעים השימושיים לפחות, והוא לכן תמיד אמר שהוא היה ממליץ למישהו שרוצה ללכת ללמוד, להתחיל ללמוד את המתמטיקה. טוב, לפחות עם זה אני הזדהיתי. עם השנים הפכתי מתלמיד לקולגה צעיר, מקולגה צעיר לקולגה, בהמשך לידידות ארוכת שנים שנמשכה עד לפטירתו ב-2017. כמובן שקשה לחזות ב-1976 כשאתה סטודנט, ש-45 שנה אחרי זה אתה תאמר דברים לזכרו של המנחה שלך, אבל זה איזשהו גלגל ענק שבאמת נותן פרספקטיבה לדברים. ואני עובר במעבר חד לכובע השני שלי. שלום, אני חושב, היה גאה מאוד בקבוצת המועמדים לפרס השנה, שהייתה בדיוק המתמטיקאים השימושיים שמייצגים את המיטב שבישראל, ובפרט אמורים הדברים לגבי זוכי הפרס, חתן הפרס ירון ליפמן. אז בקשר לפרס עצמו, שהוא ענק בחסות, צריך לציין, האיגוד הישראלי למתמטיקה, בשם חברי הפרס, פרופסור ורד רום קדר, שאני רואה אותה כאן, ממכון ויצמן, פרופסור גדי פיביך בתל אביב, ואנוכי יושב ראש הפרס. אני שמח לציין את ירון ליפמן. הפרס עצמו מציין שפרס אברבנאל למתמטיקה אנושית לשנת 2020 מוענק לירון ליפמן על מגוון עבודותיו בתחום המידול הגיאומטרי, על פיתוחן של שיטות להצגת משטחים וניתוחן התיאורטי המטמיע כלים מתמטיים חדשים, ועל יישומן של שיטות אלו בביולוגיה, בראייה ממוחשבת, באנימציה ועוד. ברכות. ובהזדמנות זו אני מעביר חזרה את המיקרופון לגדי. גדי, לא שומעים אותך.
אמרתי שתודה. שבשנים כתיקונם זה השלב שהיינו מזמינים את ירון לבמה ומעניקים לו את התעודה של הפרס, אז עכשיו נעשה את זה באופן וירטואלי, לפחות היתרון הוא שאפשר לראות את התעודה, אז אנחנו נאלץ לשלוח אותה בדואר. אז זה השלב להעביר את הבמה לירון, שנעבור לחלק המדעי של הערב. אז ירון, הבמה שלך.
אוקיי, תודה רבה. זה מאוד מרגש, ההרצאה שלי היא באנגלית. לא שהשפת אם שלי היא אנגלית, אבל אני מניח שזאת השפה שהתרגלתי לדבר על עבודות. אז ברשותכם אני אעבור לאנגלית. So I want to start with a big thank you. Thank you to the Abarbanel family and the Tel Aviv University and the Israel Mathematical Union, and I guess also the award committee and all the participants in establishing this award. I'm humbled to get it, and I'm proud, and I'll do my best to push applied math in Israel as much as I can. I want to say a few words about applied math, what it is to me. So applied math is what I see as a crucial link between mathematics and application, or between theory and practice. It's not often in the front of the stage. Sometimes it does a lot of work in the background. That's why I think it's so important to do all we can in order to kind of make applied math get its recognition also among the next generation of researchers and students and so on. Although I did my undergrads at Tel Aviv University and also my PhD at Tel Aviv, and I see many familiar faces and even names, people who didn't turn on the camera but taught me different courses. I didn't have the chance or the opportunity to take a course or work closely with Professor Abarbanel, although I was aware of him, of course. While I was preparing this lecture, I looked a little bit about the history, and here's a few anecdotes that I could collect. The first thing is that it seems that Professor Abarbanel was exactly the type of applied mathematicians that I would say kind of justify the title I gave above. He worked on a really wide spectrum of both developing algorithms, numerical algorithm for PDEs, and proving them and establishing mathematical theory to support them with great contributions. And maybe a little bit more esoteric, at least if my calculation was correct, he was the great-grandson of David Hilbert, which, for those of you who don't know, one of the most influential mathematicians of all times. And he himself is already an academic great-grandfather. again, I apologize if I didn't get the number of great exact, but anyway, I think he's somewhere is an important link in a great lineage of mathematicians. And I want to thank again for this award. I'm going to talk, my talk is going to be about somewhat of the recent works I've been doing, maybe not exactly what the citation was talking about, but I did my absolute best to make it as accessible as possible to all the people, even people who don't have much of academic background. I hope they can still get something out of my lecture. So my lecture, maybe not very surprising, is kind of revolves around the subject of AI. And I think it's a good idea to start with the dictionary definition of AI. So AI is the simulation of human intelligence processes by machines. And let me immediately give you an example. So here's a process that some would consider requires intelligence. The process is you want an algorithm. So algorithm will be visualized by this kind of wired brain. We want to insert to the algorithm maybe an image of a dog, and we want the algorithm to decide whether it's a dog or not a dog in the image, whether the image contains a dog, let's say it like that. This is the type of algorithm which requires what we would consider intelligence. And in the recent years, also, we heard it in the introduction, there is some sort of a revolution going on. There's some class of AI algorithms called deep learning, which kind of producing really amazing results in a wide range of fields. Here I just picked 3 out of gazillions examples. The rightmost 2 are actually from really the last several months. And here's the type of things that algorithm can do today. So I don't know if some of you know.
Yaron, we don't see your slides. We don't see your slides.
Oh. Let's see. You haven't seen them from the beginning? Okay, sorry. I was I'm almost finishing my lecture by now. No, I'm kidding. Sorry, so thank you, Vered. So yeah, so can you see it now?
No.
It went and went away. And it went away.
Did you see them at some point?
Yeah.
Or because I think we checked.
Now we
Okay.
see
Now we see it. Now we see it.
Now?
This is good.
Okay, all right. So anyway, let me just continue from where I stopped. Sorry about that. So I was talking about algorithms that can do intelligent things. I was giving the example of algorithm that can take in an image and decide whether the image contains a dog or not. And then I was giving 3 examples of the recent revolution. I'm assuming that you can see my slides now. So anyway, these are 3 examples that already can be seen in papers and technology around us. For example, nowadays you can, for example, type in a name in Google Photos and get all the images that contain that person, although you didn't mark any of those images that contain the person. In this case, I looked for my middle son and I got all the images that contain his images. That's maybe already not so recent news. More recent is, for example, this AlphaFold result of DeepMind, where they actually made a huge progress in protein folding. So now they can already make an algorithm predict the 3-dimensional structure of this protein with very high precision. And the last example here from the right is actually the paper that got a best paper in the biggest AI conference, NeurIPS, just a month ago. It's a language model by OpenAI. It's called GPT-3, and it's pretty remarkable. Here are two examples from people that use its API. You can basically provide it with some sort of a text, and he can continue the text or provide an answer. In this case, for example, someone wrote, again, with no preparation whatsoever, if I have two shoes in a box, put a pencil in the box and remove one shoe, what is left? And the algorithm replied the shoe. Maybe not a perfect answer, but definitely shows some sort of intelligence. I thought it will be also beneficial to go over important milestones in this revolution. What were the factors that kind of made it happen? And then zoom into the things that, to the specific field I've been working in. So deep learning is basically using a very old kind of algorithm called artificial neural networks, which is inspired by neurons. Again, there's a big debate whether it does simulate something similar to what happens in the brain. Again, it's not really something that I'm thinking about, but it's definitely something that people give it a lot of attention. So that happened 60 years ago, and then after maybe 30 years, people have started to construct computational models with those artificial neural networks, creating multi-layered kind of neurons to produce more elaborated models. And then after 10 years or so, people have started to invent all sorts of interesting architectures, what they call today architectures, LSTM, long short-term memory, and CNN, convolutional neural networks. So convolutional neural networks will have a central part in my talk. This is basically a specific type of neural network that have done a wonderful job in computer vision and computer graphics problems. And this is also a point where some of the work that I want to present is generalize these structures to other data sets. But so this is basically the algorithm for creating deep learning have been known for many years, as you see, more than 20 years. But still two components were missing for this revolution to take place. The first is the computational power. So basically what gave deep learning the computational boost is the graphic processing unit, which is, some of you know it as a GPU. It's basically can do certain tasks, but very fast. And the last component, which is very important, is the data. Okay, so even if we have algorithm, we have computational power, without the data, we cannot really achieve any learning. And about 10 years ago, people have started to collect huge data sets with millions of images labeled, and they've been used in order to put all these components together and produce a breakthrough paper by Hinton and his students, basically constructing a CNN network running on a GPU trained on ImageNet to produce really good classification rates for images. Basically, what they did is the task is to get in an image and kind of ask what's in the image. Okay, so this is kind of the framework story. But what I've been interested in is a different type of data. And the type of data is something that you can call irregular data. So irregular data is basically data that is not an image. It's not something that is provided to you in an array of numbers or a sequence of numbers. It's basically something which is more kind of unstructured. One example are surfaces. So if you think about biological objects like bones or three-dimensional scans of shapes, so these are two-dimensional manifold or surfaces. These are objects which are interesting to many researchers, and also in the technology world, a lot of applications require an analysis of such data. Another type of data, for example, point clouds. So if you think about here, it's shown in the context of autonomous driving. So we have sensor on cars, the shooting rays, and they're collecting three-dimensional points of the scene around the car, and you're interested to process this somehow, maybe separate roads from people, from buildings, and maybe classifying these things and so on. If you go one higher level of abstraction, you can think about structures like molecules. So you can think about, you have a data set of molecules with properties, you want to do some analysis, you want to learn those. I'm going to give a particular example in a few slides. And another type of data could be networks of devices of some sort or people that you want to learn. So these are examples of irregular data. And here's a motivating example for when would you like to learn or to do something with such data. So think that, for example, you want to do
Yaron, you're muted.
Yeah, someone pressed mute. Sorry. Can you still see my slides?
No.
No.
So Gadi, I think if you just give me the controls on this thing, I will make sure I'll not mute myself.
Let me make you a host. I'm just worried about the recording. I don't know what the meaning of that. I make you a host. So, okay.
Okay, can you see my slides again and you hear me?
Yes.
Yes.
Okay. So anyway, I was saying that making these experiments are taking a lot of time and maybe they're requiring a lot of money, and maybe it makes sense to produce an algorithm that is given with the experiments we did so far and can basically give us with maybe good accuracy the reaction of the tissue to new compounds. Okay, so this is basically we want to feed new compounds, and maybe we can screen or prune a lot of compounds which definitely won't work, and then we can kind of facilitate and speed our drug design discovery. That's an application, right? So that's the story. So how would you like to go about and do that? So for example, one way to represent a chemical compound, we can think about the molecules that compose it. We're going to represent it as a graph. A graph is a mathematical structure. It is composed of atoms, shown here with different colors. And some pairs of atoms are kind of joined by some chemical bond. So basically, this problem kind of motivates the task of getting a collection of graphs, maybe some of them with label, active or not active, providing some sort of generalization, and now creating a new graph and predicting whether this new graph, the compound, which this graph represents the molecules of, would have some sort of effect on the tissue. So that's like the framework of drug design with machine learning. Now, so what I've been saying so far is that, for example, molecules can be represented as graphs, but graphs can be seen as one instance of irregular data. So graphs are actually right in the middle of a certain interesting hierarchy. Below in the hierarchy, there are sets. So sets are data structure which are irregular. It just contain of elements with no particular order. So basically the colors here represent some sort of feature that comes with the elements. It could be, for example, the atom type. So sets have only data attached to the nodes. Graphs has nodes, but also has some information attached to pairs of nodes. And you can think also of generalization of this structure, which we call hypergraphs, where you can have information attached to nodes, to pairs of nodes, to triplets of nodes, and basically to any subsets of nodes. So this is really the type of data structures that we're interested in. And if you think about taking this data structure and assigning to each node, for example, a three-dimensional coordinate in some coordinate system, you get what we call geometric data. If you take a set of things and each thing is a three-dimensional coordinate, then you get what we call a point cloud, which is basically a bunch of points floating in space. That's the common output of three-dimensional scanners, for example. So, for example, you can think how do we design a function that takes in this point cloud and spits out a class, for example, that this is an airplane. If you take a graph and prescribe two-dimensional coordinates to its nodes, then you get something like a molecule, right? So you have three-dimensional coordinates, but also you have connection between the coordinates. And with hypergraphs, this is a vast generalization. You can do many things. For example, you can define discrete surfaces by putting three-dimensional coordinates on the nodes, assigning edges to pairs of nodes, and to triplets of nodes, you're also assigning adjacency relations. So you get these small pieces of planes, and this is a creature that is called a triangular mesh, right? So it's a manifold that is constructed from three-dimensional triangles stitched together. So in general, one of the main things I've been working in my lab is how to develop deep learning methods for irregular and geometric data. So how do we kind of harness the success of deep learning to process the type of data that I've just kind of shown you, the graphs, the hypergraphs, molecules, point clouds, and so on. The idea is that most of these creatures have mathematical kind of intuition and representation behind them, and this can be exploited to design efficient deep learning methods. But in particular, we have been looking at two approaches to this problem. The first approach is to use symmetry, which is a really a core kind of a concept in mathematics and physics in order to design these things. And I'm going to show that first. And then I'm going to show another thing which is very popular in math and applied math, which is implicit representations. So this is another something that kind of works really well for deep learning and irregular data. By the way, I didn't say I would be happy to take questions at the end. I promise to answer all the questions to the best of my ability. But just to keep things flowing, I will defer questions to the end. So we start with symmetry and equivariance. And what I'm going to do now for the first couple of slides, or maybe 3 or 4 slides, I'm going to review the successful deep learning techniques, which is called convolutional neural networks, from the point of view of symmetry. The reason I'm going to do that is because the story of the things that we developed in the lab, which is for graphs, is really a kind of generalization of this story. And anyhow, I think it's really good idea to understand how these convolutional neural networks came to be. I hope that most of you haven't heard this story, so at least from this perspective, so it will be interesting. So the idea again in learning images is to come up with a function f that takes in an image, for example, an image of a cat, and then produce a probability of the image containing a cat. So mathematically, we say we're looking for a function f. The dimension of the domain of the function is very big. It's the number of rows and columns of the image times maybe the channel. So if this is a colored image, it's RGB. So we have, I don't know, 30,000 variables. So it's R Euclidean space with 30,000 dimensions. And we want this function to map to the segment 0, 1, providing the probability of the image containing a cat. Okay, so it's a very, it's a function from very high dimensional space. Now, the deep learning, so some of you might have asked themselves, why do we say deep learning? What's so deep about deep learning? So I think the deep learning model is basically comes from the following construction. So how do we construct the deep learning model? So it's actually very simple. It's basically taking a simple model, which I'm going to say what it is in a second, and composing it again and again and again in many layers. The deep part is basically the fact that we're composing many such layers. The layers are extremely simple. So each layer in a deep learning algorithm composed of a linear or affine transformation with a matrix. So X is the input to the layer. You multiply it with a matrix A, which is parameters of the model. These are the things we're going to play with. You add something that is called bias, but again, it's just a constant vector. It's again a parameter of the algorithm. And then you take this output and you apply some nonlinearity, which is non-learnable. For example, hyperbolic tangents. Or a very popular choice is the rectified value. It's like taking the max of the value with 0. So things which are nonlinear but extremely simple and are not learnable. And now you take the entire A and B from all the layers. So each such layer contribute to the model the parameters A and B. And now there is some method to tweak those A and B in order to achieve something. For example, being able to predict well the task on the training dataset. Now, the big problem is that if we want to do this for images, then let's assume that we just, even the first layer, and we want to keep the dimension of the input. So we want this matrix A should be in the dimension, the number of degrees of freedom there is the number of the input dimension, which is 30,000. And let's say we want to keep the dimension. So we want to output something of dimension 30,000. So the size of A is already billion parameters, which even though we're doing crazy things today with a huge amount of data and memory, this is already way beyond what we can do with computers today. We cannot really afford 1 billion parameters in just a single layer. So people have thought hard how to adapt these models to images. And it turns out that symmetry was the key in order to make it work. Symmetry is what made it possible to reduce the number of degrees of freedom, but maintain the expressive power of these models. And here how it works. So what is symmetry for images? So the main observation was that if you take an image and you just translate its content, okay, then you are not radically changing the objects in the image, okay? So you can denote this transformation by T. T will be actually the way we want to denote all the transformations. So if you understand and if you all agree that that's the case, then we can say that we want our function to be invariant to these symmetries, to these translations. Mathematically, it would mean that the function would output the same probability or the same class for both these images. So you can say that you want f to produce the same value for t of x as it does for x. This is called invariance. Okay, so once we understand that's what we want, let's see if it helps us in terms of degrees of freedom. How do we incorporate it in a deep model? So it turns out it's also kind of intuitive, but if you constrain your first layer to be invariant, then everything you do after does not change the invariance property of the network, right? Because if the first layer is invariant, all its outputs are invariants, and then you can do whatever you want afterwards. So the question really is, how do you choose A and B so that the first layer, which is a very simple function, is invariant? So mathematically, you want to ask, how do I choose this transformation L? So let's think about just the linear part without this bias, this constant part, such that this diagram commute. So applying transformation and then L would always lead to the same thing as applying L. Now, if you think about it a little bit, since using translation, you can take any pixel to any pixel in the image, what you really get is that the only L that satisfies this thing is the constant, meaning that you pretty much all you can do with an invariant layer for images is summing up all the pixels, which means that both these images that I'm showing here at the bottom would always yield the same result, because the right image was constructed by shuffling the left image. So even if you didn't follow the exact explanation that was just given, the bottom line of this slide is that just going directly with invariance doesn't give expressive enough models. It cannot really do anything interesting on images. And it turns out that the one thing that made this thing work is something that is called equivariance, which is a little bit more sophisticated idea of how to use symmetry. But this is really the notion that is being used and making all the heavy lifting in modern deep learning, at least from my perspective. But I think many would agree with me. So it's not like I'm not the only one who thinks like that. So what does equivariance mean? So equivariance means that it doesn't cancel symmetry, it just respects it. Mathematically, it means that our layers commute with the symmetry. So basically, equivariance means that applying the translation and then the linear transformation would end up with the same result as applying the linear transformation and then the translation. So we say that basically our symmetry and the linear layers, the linear transformation commute. Now, for translations, we all know what are the operators that commute with translation. These are the convolutions, right? And that's it. You can actually define convolution, but all the linear transformations, that would commute with translations. So basically what that means is that if you take convolutions, you're guaranteed to commute with any translation in the input. And this what led Jan LeCun, and actually there was also other version in the history, to construct the convolutional neural network. So what they suggested is to stack several equivariant layers, then a single invariant layers, and then whatever. Whatever means a general deep learning, or it's called multi-layer perceptron at the end. And what I first want to convince you that this structure is indeed invariant. If you mark the hidden layers as variables y1, y2, y3, so for example, y1 would be input of the first layer, and the y2 would be output of the second layer, and so on. So if you feed t of x to the layer, it would commute with the different, sorry, did you see that? There was a sort of small animation here. Sorry. I was not sure if this animation. So instead of x, we're plugging in the translated version of x. Since t commutes with every layer, it kind of changes place until it reaches to the end, and then the invariant layer kills this t. So in total, we get an invariant network. So this is a way of constructing invariant functions. Okay. And now so that's basically an introduction to convolutional neural network, which is again the main working horse in model deep learning algorithms that do image processing. And now I'm gonna show you how to take this point of view and adapt it to graphs. Okay. So again, the idea was the model or the framework or the story would be, let's say we want to do drug design, and someone gives us a lot of molecules that have been tried in the lab with certain results, for example, active, non-active. And our task is to generate a function that takes in a graph and spits out some probability of that, the compound consisting of this molecule being active or not. And we're going to test our result later on a bunch of unseen molecules. Okay, and then we can evaluate whether we're doing a good job or not. So the main question is, how do we construct such function on graphs, and how are we making sure that our functions are well defined on graphs, right? So the first thing that we're going to do is ask ourselves how to represent graphs in a computer, right? Graphs I'm kind of visualizing at circles and connections. So the first thing that we're going to do, we're going to use a representation with matrices. So for example, this graph is going to be represented by this matrix. We're going to enumerate the nodes in some order. And then on the diagonal of the matrix, we're going to put whatever information is attached to the nodes. And outside the diagonal, we're going to put on the adjacency relations in the graph. So for example, if you think about this green node, which was labeled here as the third node, but that carries no information. But this green node is connected to all the other nodes. This is shown here by these black kind of turned on spots in this matrix. So this node is connected to all the other nodes. And all the other edges are missing. So in some sense, I hope I convinced you that this matrix represents this graph and contains all the information about it. Now, when I did that, I made an arbitrary choice. I ordered the vertices somehow, because computer doesn't know what is a set, right? I have to, put something first, then I have to put something second, and so on. So I made the choice of putting this vertex third, but that carries no importance. In fact, these are the same graphs, okay? I'm just enumerated them differently. So here's the symmetry. So we ask ourselves, what is the symmetry in representing graphs? This is, by the way, the notion of graph isomorphisms from computer science. Basically, all the ways that you can permute the nodes would result in the same graph. So these two matrices, right, although they look different, they represent inherently the same creature. How do we get from one creature to another? If we take the permutation that was used in order to permute the nodes, then conjugating the matrix with this permutation would lead to the same representation. So the symmetry of graphs are conjugation by the same permutation. That's the symmetry group of graphs. It's the same symmetry group as permutation with a slightly different representation. Just for notational simplicity, we're going to denote it by P, which is a permutation, and dot. So dot would mean you apply the same permutation to both the rows and columns of this matrix. And now we are ready to do the same kind of things that was done before. If we want to define convolutions on graphs, then we can ask what are the linear transformations that commute with this permutation. So if you do permutation the way I just defined it, and then linear transformation, or apply the linear transformation and then permutation, I end up with the same thing. Mathematically, we can write down this equation, right? So we're looking for linear transformation on matrices, and then we apply the transformation, and it should compute like the same thing as doing the permutation and then the linear transformation. So the first result that we did in this aspect is basically characterizing this space of linear transformations. And in fact, it can be done in a more general setting. So here we're working with matrices, which are two-dimensional tensors. But you can think about hypergraphs, as I said briefly before, if they can be thought of higher dimensional tensors. Then you can think about equivariant layers between different order tensors. So if you want to think about a tensor of dimension k and tensor of dimension L, the linear space of linear equivariant transformation has the dimension Bell number of k plus L. Okay, let me parse that. So k and L are the input and output order of the tensors. So in case of graphs, k equal 2, L equal 2. So it says the dimension here is Bell number of 4. The important thing about this Bell number, which I'm going to show you in a second, is the fact that it's independent of n. So regardless of the size of the graph, how many nodes are in the graph, the number of basis elements always has a constant size, which is a good news. It means that you can learn something of one size and apply it to other size. For the specific case of graphs, which I discussed before, again, we're talking about matrices. So we plug in k equal to L equal 2. So we get that there are exactly 15 different bases. So it turns out the Bell number of 4 is 15. What is a Bell number? A Bell number is a combinatorial number. A Bell number of 4 would be all the possible ways of decomposing a set of 4 elements to subsets. So here I even do like an illustration that shows all the possible ways to do it. For example, putting each element in its own set, putting these two in a single set and these two as singletons, putting all of them in one set. So these are all the possible ways enumerated. Of course, this number grows very quickly with k and L, but it's constant in n. It's actually, this theorem says a little bit more. It provides a dimension, but also comes with an orthogonal basis of this space of transformation. And you can actually take this basis and construct networks with that. So here's the network. Again, in the spirit of the classical CNN, you stack in several equivariant layers. So each of these arrows have 15 degrees of freedom times the dimensions of in and out. And here the last invariant layer has 2 dimensions. I didn't mention that, but invariant functions of graphs have two basis functions. And now you can do exactly the same as convolutional neural networks. And basically you're able to design networks that work with graph and hypergraphs in a complete principled way. I think I want to kind of wrap up this part by kind of saying what followed this work. So basically, interesting question that we and others have worked on is what is like the expressive power of these models? It turns out that they have intimate relation with message passing algorithm, which was the common thing that people was doing with graphs. And it turns out that if you use higher tensor order, you get more expressive power. Another interesting thing is that you can trade tensor order with more complicated layers. So instead of linear, you can take quadratic. One notable quadratic equivariant function is matrix multiplication, which turns out to be very effective in this context. And in terms of applications, you can use these things to do things like take a model function from sets to graphs. For example, in particle physics, it turns that it's very interesting to take in observation in colliders, which are sets and coming up with clusters of these observation to kind of cluster them to the particles that they came with. So there are really interesting applications for these methods. So I have now the second part. Gadi, I'm not sure how much time I've used so far.
I think you have like 5-10 minutes. I'll stay here, so I assume everyone else. So I'd say 5 to 10 minutes.
So I can. Okay, I'll use 5 minutes more, and then we can take questions if that's okay. Okay, so I'll do this part relatively quickly. I want to show you, like, just to give you kind of an orthogonal view of deep learning of geometrical data, which I think some of the applied mathematicians in the crowd also can relate to. So one popular way in mathematics to represent geometry is using implicit representation. So if you think about functional representation, when we work with functions, we provide values. And then, for example, we can come up with a function that gives a positive values on the plus signs here and negative value on the minus signs. And then somewhere implicitly, the function kind of crosses the zero value, right? Another way of thinking about this is, let's say we're given examples and we know that these examples come from a one-dimensional curve. Then we can come up, instead of using the functional setting, we can say we want to use our model, in this case, a neural network, and we're interested in the zero level set of this network. So we're not going to use this network just by putting in a number, getting an output, but we're really interested only in where this neural network crosses zero. And the interesting thing about that is that if there are some condition about the gradients of this function on the crossing, then this thing will represent manifolds in the proper sense. Okay, so that's like the overall story. One major application is surface reconstruction. You're giving a bunch of points floating in three-dimensional space, and your goal is to come up with a surface that these points were sampled from, or kind of predict the surface. So one way to model this is to come up with a neural network. And this neural network, the zero level set of this network, all the x's such that the neural network gives the zero on, would define a two-dimensional surface that would be defined as the solution to the problem. It's really interesting to see how this thing interplays with PDEs. Here's a really simple algorithm that really magical work on this problem. So there is this famous nonlinear PDE called iconal equation. The iconal equation basically takes a bounded domain and asks that on the boundary of this domain, for example, this L shape, the function would zero out, and everywhere else, the function should have the gradient norm of 1. Now, this equation doesn't have a unique solution in the standard sense. There's something that is called the viscosity solution. But anyway, in the viscosity solution of this problem is the distance function. Okay, and if you solve it, so here is a visualization. Here inside, it's the minus of the distance function, and outside is the plus of the distance function. And what you can ask yourself is what happens when you kind of break the rules of a partial differential equation, and instead of taking bounded domain as required by the viscosity theory, you actually take the punctured plane. You just take a bunch of points. So you're asking, you want to solve the PDE such that it's zero out on those bunch of points and the gradient equals 1 everywhere. And of course, this is ill-posed problem, right? Because, for example, here are two sine distance function, both of them perfectly solving the PDE, right? Now, it turns out that in the optimization process of deep learning, there is something that is called implicit regularization. It's something that people are really interested in the last couple of years. And it turns out the optimization process of deep learning tends to add a regularization to the process of optimizing the network. And here's a really simple experiment. If you take this data, this point sample from a straight line, and you type in a loss function. So a loss function is something that you want to optimize when you optimize deep learning, and that's basically you're doing some sort of a gradient descent in order to minimize that thing. So you want your network to zero out on the input points. In this case, these are just the white points, and you want the expectation of not satisfying the Eichenal equation would be also minimized. And if you just optimize this, even if you take a very complicated model, the result will actually be this. So this is not a linear function. So the thing that created this thing is a really complicated neural network that can represent crazy lines. And this phenomena also continues when you take other stuff. So here you take just some points from a circle. And what you see here is the solution of this simple optimization problem on the top. Now, there are many, many, many local minimas to this creature, which look horrifying. But somehow you end up with this solution. In the right, we even took a random sets of points. And even in the random sets of points, it came up with a kind of a reasonable solution. So this is the type of phenomena which I think is very interesting. It kind of uses some sort of implicit regularization of neural network to drive the solution into those into these nice locations. I just want to show you an application of this thing. So here's, by the way, you can learn really complicated sign distance function of three-dimensional structures. And here is, for example, you can use this thing since it's the context of you can do it on many shapes simultaneously. You can take a collection of human body shapes. And here you actually see when you learn several sign distance function in this way, and you just basically do a regular average, these algorithms are able to produce kind of a semantic averages between shapes of human bodies. I just want to mention this slide thing in 1 minute, and I'll be done. We can also use this implicit representation in order to try to tackle more classical problems in computer vision. For example, the problem of taking in a sequence of images and figuring from the images the geometry of the objects inside the images, their appearance, material and light, and the camera location. So I'm not gonna describe this algorithm too much. I'm just gonna say that the way we represent the geometry is by using, again, this implicit representation, and this is provide a really flexible and expressive model in order to do that. And here is the result of this algorithm. That's my last slide. So you can see here, that's basically the output of the algorithm. The algorithm is getting as input a bunch of images. It figures out the geometry of the object in the image. And it even can generate it from unknown views. So these views are not seen in the data set. And it does it with really high realism. Here on the bottom is actually an object even with harder material and light. And how do you know that something really interesting happened? Because now you can ask the algorithm to switch the materials of these two things, even though in your training set, there were no such examples. So in this training set, we never saw a golden skull or a bone-like bunny. But somehow the algorithm was able to disentangle this material and geometry in a way which allowed it to produce an image in the format, in appearance that was not shown in the training set. That's it. I just want to say thank you to all the students that did most of this work. And again, thank you to the committee, to the Abarbanel family, and all the people involved. Thank you very much. I'm happy to take questions now.
Yaron?
Yes.
So maybe I'll continue in English since the lecture was in English. Thank you for a nice talk. So let me just ask you, with regard to the second part, talking about the loss function, where you have the addition of the point values and the least squares. Yeah. Is there, and if so, how do you do it? A weighting parameter between the contribution of these two contributions for the loss function.
So the only thing, definitely there is a parameter here. The only thing I can say, which is well justified, is that if you think about the linear model, which you can say is not a good representation of general networks, but for linear model, even if it actually doesn't matter which parameter you give it, it will always converge to the linear sign distance function with probability 1. Probability 1, why is the probability here? Because there is the initialization of the network. But other than that, it's a really interesting question how to set this thing, which we don't know the answer to.
So what you showed here is sort of idealization. There is a parameter which actually gives the right weighting between the two contributions, the expected value and the data. And there's a question how you quantify this parameter.
That's correct, yeah. In some sense, in order to get a sign distance function, you really like to zero out both of these losses, right? It turns out in the linearization case, you can actually show that these two do not fight each other, and they actually both reach the global minimum. But for more complicated models, this is obviously not so easy to show. Although in practice, it happens all the time. So it's a really, one of our roles in applied math is also to entice other people to, or find out interesting questions that we don't know the answer to. So I think that's an interesting question as well.
Thank you.
Any other questions? I see some of my lecturers from the undergrad, so I can now pay back by asking them to ask a question. 20 years payback. Okay, Gadi, I think there are no more questions, so I can give back the mic to you, the virtual mic.
אוקיי, תודה ירון על ההרצאה המרתקת, תודה לחברי ועדת הפרס, לגיורא, למשפחת אברבנאל, לכל מי שיצא מהבית בגשם הנורא לפני הסגר ובא להרצאה הזאת. תודה לכולם, ברכות שוב לירון על הפרס, ונתראה בעוד שנתיים באברבנאל 22, אז ערב טוב לכולם.
ערב טוב, תודה רבה.
תודה רבה.
תודה ירון.
תודה רבה לכל מי שעסק בארגון.